Okay. I want to go back to physics class because, in a very real sense, one of the purposes of calculus is understanding and explaining physics. So, Newton's laws of motion. Well, Newton's laws of what are Newton's laws? There are three of them. I'm looking in particular for the second one, if anybody happens to know them. Newton's laws. An object in motion will stay in motion unless acted on by an outside force. An object at rest will stay at rest unless acted by an outside force. That's the law of inertia. That's the first one. There are two others. Same rule. That's still the law of inertia. Object at rest will stay at rest unless acted on by an outside force. There's rule 2 and rule 3. You have the internet. Second law, third law. That's Newton's second law. The third one is for every action, there is an equal and opposite reaction. Now, personally, I think about this rule and I say to myself, acceleration is a derivative. It's not just any derivative, it's a second derivative. So force acting on an object. That's 1 and 3 tell me force does stuff to things. Based on this idea, what are the appropriate units for force? My unit for force. What's a Newton? Gotta be expressible in terms of my fundamental units, right? Fundamental units in this case, kilograms for mass, meters per second squared for acceleration. That's in SI units. But if I'm not in metric, then my units are pounds. Pounds is what we think of as weight, right? If I asked you, how heavy is this textbook? You tell me it weighed, I don't know, 4 pounds. But that's technically the force it exerts downward due to the acceleration of gravity. In the imperial system, there is a unit of mass, not force, that would do something like this. A pound is technically 1 slug times feet per second squared. And the force of gravity is 32 feet per second squared. So a slug is the mass that weighs a half an ounce. Nobody uses slugs, ever. We think of weight, we think of force. So let's assume my book here weighs 4 pounds. I am preventing the book from falling to the ground, yes? What happens when I move my hand? Right? Why? Gravity does what? It exerts a force on the book. If I hold the book on the table and I push to the side, the book slides. I exert a force on an object. When I exert a force on an object, I'm doing work. I cause the object to move when I push it across the table. Gravity caused the book to fall down. The work done is the product of the force exerted times the distance the object moves. So if I take this 4-pound book from my shoulder to overhead, I've moved it, 2 feet. How much work did I do? I'm going to go with not very much, but how much actual work did I do? 8 what? Yeah, I did 8 work. Say again? I'm not in metric. I'm in pounds and feet. And literally, I'm multiplying pounds by feet. The unit here is called a foot-pound. You will more often see this unit when referring to work done rotationally. Anybody ever change a tire on a car? Get a flat, change tire? There's a wrench that you're supposed to use that exists a certain amount of torque on the nuts on a car tire. Torque is a amount of work. It is measured in foot-pounds. Now, if I'd done this entire problem in kilograms, 4 pounds is roughly 1.8 kilograms. 2 feet is roughly 60 centimeters. There you go. Same exact problem. How much work did I do? There's something missing from this version of the problem that was present in the previous version. What's missing? Neither of the previous problem didn't have a time in it either, right? There's no time in that first one. There's no time in the second one. When work involves time, we think of power. The amount of work done over a certain amount of time, well, then I'll divide and I'll get like power is work done per second or per minute. As a matter of fact, We usually think of it as energy expended per minute. And most physics classes in metric, we call that joules. More on joules later. What's the answer here? Two problems. Where'd you get 108 from? Okay, so if I multiply those two like I multiplied these two, right? But this number, this 4, is pounds. Pounds is force. Kilograms is mass. What's missing here is an acceleration. This 1.8 kilogram mass is exerting a force. The force is due to gravity. I need to include to get to force. So if I want to multiply, I need to multiply the 1.8 times 9.8. That gives me kilograms meters per second squared. That gives me newtons. I don't have force otherwise. The other thing I need to do, Chase, is I need to make sure I'm in common units. This is in meters per second squared. That means this needs to get converted to meters. So I have to do two conversions. I have to convert to force, and I have to convert to common units. Okay, well, now I can actually do the work. What do you get? And that is in Newton meters. Or kilogram meters squared per second squared. It's kilogram meters per second times meters. I have to remember to make sure when I'm in metric to make my mass into force. Questions? A lot of these problems are done in non-metric units strictly for the reason that I don't have to do that conversion. So you'll see a lot of things in pounds and feet simply because that's easier. But I just have to remember if I'm ever doing anything in metric, I have to multiply by 9.8 somewhere in there. What if either my force changes as I move things, or my object changes, or the distance changes? let's consider a fairly easy chemistry situation. If I have an object at the origin, and I'm going to make this object a positive charge. Maybe it's a proton, a hydrogen nucleus, right? Here's a raw proton. Positive charge. And then I've got another one sitting here. One unit away. What happens to two like charges? They repel each other. They push away from, aha. I'm going to hold the one at the origin, and I'm going to let go of the one at one. It's going to go that way. Whee! Now, technically, the equation that goes here has some numbers on it. It's got some constant of electrical charge, K. It's got the amount of electrical charge on the first proton and the amount of electrical charge on the second proton. I don't remember what any of those numbers are. So I'm just going to set them all equal to 1 for the moment. But what I do remember is that the force exerted is reciprocal to the distance between the two items. I believe the actual formula looks like that. If you've taken a physics course, that might look familiar, where K is some constant of electrical permittivity, and Q1 and Q2 are the respective charges of the object, and R is the distance between them. I just don't know what any of these constants are, so I'll make them all 1 for right now. I want to know what happens as this object ends up here. Problem is, as I get further away, the force changes from place to place to place. So let's think about what happens if we're at some particular spot, somewhere between 1 and 4. Let's say I'm here. As a matter of fact, I'm going to consider the width of that little box that I just drew. And I'm going to say I move from one side of that box to the other side of the box, a teeny little step in the x direction. And on that step, the force was effectively a constant. So I could just multiply the force times that little bitty bit of distance. That little bit of distance is in the x direction. So let's make it a change in x. Aha! I could cut up the x-axis into a bunch of pieces and use this sort of approximation, couldn't I? And if I did this approximation, I would then have to add up the force times each of those distances. And I'd have to add up however many of them I did. Let's do n of them. And on each one of those, I'd have to pick a value for the force from somewhere in there. So this just wouldn't be some f, it'd be f at a particular point. Wait a minute. I've seen this expression before. What kind of an expression is this? We did this on Friday. We did this on Thursday. We did this on Wednesday last week. It's a Riemann sum. And if it's a Riemann sum, I can let more and more rectangles happen. And if I let the limit as n goes to infinity, this becomes an integral. If my force changes, instead of multiplying, I integrate. Well, notice I have a function of x right here that is my force. And I know where I'm starting my movement and where I'm ending my movement. I start at 1 unit. I end at 4 units. If I want to know the total work done by a changing force, I just have to integrate. So in this particular problem, I have to do that integral. Please do that integral. The downside to this problem is I have no units. So I'm going to assume that everything I need is in here because it actually did give me force and distance. I'm going to assume everything's in the right units. So what do I get for this? I don't know if the right units for this are Newton meters or foot pounds or whatever the appropriate unit is in a different system. But I have this force over this distance, and the force changes. So instead of just multiply each little step and add them all up, that's what an integral is. I find writing the Riemann sum helps me understand what's going on here. But you all are looking at me like either I've whizzed in your cornflakes or you'd rather be anywhere else but here. And I can't quite tell which it is. Questions? If I had a cable that weighed 200 pounds and I wanted to move it 100 feet straight up, how much work would I have to do? Here, there's a coiled up cable in a box. There's a box weighs 200 pounds. You got to move it 100 feet that way. How much work do you do? Say again? 2,000. I just multiplied the two numbers, right? 200 times 100 is 20,000 foot-pounds. Now, let's change this slightly. I have to pull it up 100 feet from the roof where it hangs over the edge. I'm at the top of a tall building, and my cable is hanging. My building is higher than 100 feet. The cable is 100 feet long. I'm on the roof, pulling up this cable. How much work do I do pulling up the cable? The answer is not 20,000 foot-pounds. Why not? Okay. Gravity is already included in this because I'm in pounds. If I was in kilograms, I'd need gravity. But if I'm in pounds, foot-pounds is my right units. Why is the answer not 20,000 this time?
There's a more stacking on already. So it's like
The only force that's acting on it is gravity. That's the same force that was acting on when it was in the box. But when I moved the box, the whole cable went the whole 200 feet. Part of this cable is almost at the roof already, isn't it? Part of this cable is 100 feet away. But part of this cable is in between. So the difference this time is that not all of the cable goes all 200 feet. Last time it was the force that was changing. This time it's a distance. So I'm going to do this the same way we just did the last problem. I'm going to build a Riemann sum, but I'm going to pick a piece of cable. So somewhere in there, let's cut a section of the cable. In our minds, I don't actually want to cut the cable. I have a little bit of cable. I don't know how long this cable is. This bit of the cable. I know the whole cable is 100 feet, which means I could think of the roof as point 0 and the bottom of the cable as point 100. I don't know where this particular bit of cable is. So I'll give that an X value. I need to know two things. I need to know the weight of this piece of cable, because that'll be the force. And then I need to know how far it has to travel. Force times distance, that'll give me my Riemann sum. So first question, how far does this piece of cable need to travel? How far has it got to go? It's at X. Where is it going to go to? So it's got to go up there. So it's got to go this far. The number 100 minus X that you've given me is this distance. I need it to go this far, right? We're going up. So I actually need it to go X feet. It's got to go from X to 0. What is the weight of this piece of cable? That actually is something I don't know yet, because I haven't answered an important question. If this is my slice of cable, is it a big slice or a little slice? I get to decide how big the slice is, right? Like I did with the slicing on the x-axis. How do we decide the slices? Oh, that was my little change in x. Notice where this slice goes. It goes down the x direction. I could make this slice 5 feet long. I could make this slice 3 inches long. But it's going to go in the x direction. So this slice is a change in x. That's in feet. I want pounds. How much does a foot of the cable weigh? £200 for 100 feet. Each cable foot is, okay, wait a minute. That means that it's 2 pounds per foot times the number of feet. This is the number of feet of my piece of cable. So we're doing 2 pounds per foot. Force times distance. Since I'm multiplying, it doesn't matter what order I multiply in. If I do this as a Riemann sum, I'm going to get an integral. The only question is, what are the bounds on that integral? What is the smallest distance any of my cable needs to move? Because there's a piece of cable at the roof, right? What's the biggest distance a piece of cable needs to move? There you go. If I integrate this, I get 10,000 rather than 20,000. Foot-pounds. An interesting note, you'll often see this abbreviated rather than foot-pounds as pound-feet, in which case you'll actually see it written like that. LB is the abbreviation for pound. Does anyone know why LB is an abbreviation for pound? FT I get, feet, but why LB? Anybody's birthday in late July, early August? Anybody know the zodiac? LB is short for Libra. Libra is a sign in the constellation Libra. In the zodiac, what is Libra? It's a scale. And the way you weigh something is to put it on a scale and put a weight on the other side. The weights were called librum. The thing I use on my scale, librum, LB. The crap you learn learning Latin. There are lots of examples of force applications. I know you'll do this one when you take physics if you didn't already. You'll do spring compressions. Hooke's law. Hooke's law tells me that the force exerted by a spring is proportional to its displacement from its resting state. So Hooke's law actually tells me that F is equal to some constant times X, where X measures the change in position of the spring. I'm measuring X. In the initial position, my spring is at rest. It's neither compressed or extended. That's its natural position. And then I squeeze it in. Now, the force that's exerted is usually in the other direction. So quite often this K is given a negative number because the force will be pushing that way. It's a restorative force. If I extend the spring, then the force would go back the other way. So sometimes you'll see this written minus kx to take that restorative idea into account. So if I actually, the first thing I have to do when I get a spring is I have to measure the spring constant. Normally what we do is we take the spring and hang it vertically with nothing on it and measure the length of the spring. Then you hook a weight to the bottom, say 100 grams, it stretches, you measure the change. Then you can figure out what K is. Then you take the spring, you lift the weight, you let it go, and it goes boing, 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 right? All of that can be turned into how much work is done. Emptying a tank requires me to move the objects that are in the tank. Here, example 5 on page 470 talks me through removing water out of the top of a cone-shaped tank. Why would you make a tank in the shape of a cone? Maybe you got tired of digging and kept digging smaller and smaller and smaller. Or maybe you're using the outside pieces here as filtration. If you've got water seeping into this tank, as water seeps in through rocks and sand, it gets clean. So this is a filtration device to get clean water. You dig down until you hit the water table and line your pit with clean sand and clean rocks, and clean water seeps in. The way you build a well. And then you put a pipe down it and you start pulling water out the top. How much water? Well, we think of a slab of water, a little slice being moved up. They're going to build my Riemann sum in this problem. I am of the opinion that designing this as a Riemann sum is the most effective way to do these examples. You should read the remaining examples in this section. I will see you all tomorrow. Have a wonderful rest of the day.